much for coming. My name is Melody, and I lead a company called Observable with my co-founder and friend, Mike Bostock. You may know Mike. He created D3, which is an open source data visualization framework. And I'm super grateful to work with everyone on the Observable team. So I've been in software all my career, developing at startups and enterprise companies. I was at Google for quite a bit of time. And the thing that I was really passionate about this point in my career is how we help developers become happy and productive. So I was working on a bunch of developer tools, billions of lines of code, builds and tests, how you run services at scale and understand what's happening with the software. Observable is a magic notebook for exploring data and thinking with code. And most of our users are developers. So I'm super passionate about how visualization can help us as developers be smarter and move faster and have a greater understanding about the code that we're writing. So today, I'm going to make a case that visualization of software is an essential tool for us as developers. And many of the examples that I'll show you today come from community members in Observable, so other developers that are trying to use visualization for software. And I hope that you walk away with the basic knowledge of a few powerful code visualization tools, maybe some things you haven't seen before that you can use immediately. Sound good? Yeah? Okay. Survey time. How many people here write code the majority of your day? Raise your hand. Nice. How many people worry about managing people that are writing software and maybe making cases for better software development? Raise your hand. Awesome. How many people have created visualizations before? Nice. All right. The challenge is ahead. I need to show you some new stuff. Okay, well, I hope to share a bit for everyone here. Every business is a software business, and there's some CEOs that kind of adapt and play around with this quote, but I think it summarizes how successful software has been, right? Software is transforming or in the process of transforming every industry, every domain, every business. So why does this matter for us? I present this formula for your consideration. More developers means more collaboration, which can equal complexity. So we as developers can't underestimate the impact that our community has on software complexity. So it's no surprise that complexity is increasing, right? And complexity has a real cost for us, both in terms of correctness and speed. So complexity challenges correctness in that the software may not be doing what we actually think it should do or expect it to do. It's often unstable or buggy or insecure. And there's a lot of examples, but we can think of some big ones, right? Like EventStream or Heartbleed or the 737 MAX. There's plenty of evidence that shows when we don't understand what our software is doing, it can cause real damage. The second part, which we probably all really care about, is that complexity can slow us down. We have more dependency, big software projects, they grow quickly and they become unwieldy. And that means we can't move fast to ship features. So complexity, it's painful, right? It hurts. These are some words of wisdom from Nancy Levinson. We are attempting to build systems that are beyond our ability to intellectually manage. So if we don't do something to improve how we develop and understand software, the complexity is going to overwhelm us, if it hasn't already. And that cost that I was just talking about, it doesn't occur all at once, right? It takes time. It creeps up on us slowly, over and over. It's insidious. Any Brett Victor fans in the audience? Anyone? Oh, thanks. I'm a big fan. Okay. The power to understand and predict the quantities of the world should not be restricted to those with a freakish knack for manipulating abstract symbols. Manipulating abstract symbols. Isn't that what it means to write code? It's kind of crazy to think about. But by symbols, he doesn't mean that we're manipulating the outputs of our program directly, but instead we're working in abstractions. And these abstractions are really powerful, but sometimes they're difficult to grasp. So bring together like an ever-growing set of complex abstractions, and we as developers, we need superpowers as opposed to just this freakish knack that we may have to write code. Okay, so I'm going to go back to that formula, developers, collaboration, complexity. Okay, so let's talk about the humans, right? We heard from Octoverse, 40 million developers, more developers, many more people writing software, right? It's just not a couple more or a few. And with every industry investing, we can expect the population of developers to continue to grow. So it's not a coincidence that software developer was named the best job of 2019 by US News, or predicted by many industry analysts to be the #1 job across all vertical markets by 2030. And we're at GitHub Universe, right? Think about open source. Open source has won in the past 5 to 10 years. Over 50% of enterprise say they're using some sort of open source software. Today's software, it's either open source or it's built on it extensively. And this means that we as developers are more dependent on code written by other people, or we're more likely to share the code that we've written. So many more humans writing code, there's more ramp up for all of us, maybe bigger teams, larger software projects, and distributed teams. So let's go back to the beginning. Hello world, right? Simple software that we write. And my point here is that developing software, it's creative and it's iterative, right? It can start simple and grow quickly to be complex. We have an idea as a developer, we iterate, and that guides our creation. And sometimes we don't know exactly what we're doing. We don't know what we should do. We make it up as we go along, right? We tinker, we use trial and error, we test our hypothesis. And the more creation that we do in software, the more change there is. So hello world quickly becomes hello churn. More developers, more collaboration on software, more complexity. You know, there's significant duplication and fragmentation in the ecosystem that we have to search for tools and different frameworks and different libraries. And so we often don't know what to use when. The tools that we're dependent upon are released frequently, so we have to spend more time learning how to use other people's code or teaching them to use ours. So there's more churn in who and how much software is being written. But we don't write software alone, right? We don't write it for ourselves. So our programming should favor collaboration. And we need to have different ways to collaborate. We need to move beyond just static text files. Okay, but let's remember some other important factors too. Our brains, right? Time, it's finite. We want to make best use of both. So, Don Norman, I'm familiar with Don Norman. He's the father of cognitive design. He has this quote which I love. The power of the unaided mind is greatly exaggerated. It is things that make us smart. Okay, so if our minds need aids or tools, what does that mean? I mean, we don't design new aids or tools to perform mundane tasks, right, or automate away our toil. I mean, we do that, but we also want to build tools that actually have the capacity to make us smarter. So what is he talking about, things here? Well, you can look to writing as one of the most successful cognitive tools or things. And that's why we write source code, to produce programs. So this is my case for why we as developers need better cognitive tools. Okay, so let's start talking about visualization. Visualization and graphics more generally are powerful tools for thinking. We should have them directly available to us in our programming environment, to understand our software, to review it, to explain it. And visualization, it's a means to an end. And that means it's to insight for us as developers. We generate ideas to improve our research and our software creation. We gain insights to make better decisions. And we explain things to support learning and teaching. So before I show you some examples from the community, I just wanted to show you the notebook that I mentioned. We're using JavaScript, right? Very popular language. The code is running automatically, so you get instant feedback. You can add interaction to explore the diagram, and you can have access to your libraries and favorite web technologies. So it's going to run fast, but this is an example of creating a world map using D3. So you can modify the code, you can add components to interact with the visualization, and this is the interface behind many of the visualizations I'm going to show you today, again, created by members of the community. And you can see here, the code kind of ran quickly, but we have ways to interact and change the visualization as it's being created. So my invitation to all of us today, I have half an hour more of your time, is let's be smarter developers together. Visualization, it leverages our human visual system to help us think. But what does it mean to be smarter? As a developer, as an individual, as a member of a team, visualization helps us be smarter by exposing the underlying data and code to allow us to question, to explore, and to derive new insights in our software. And we can use it to better understand those, abstract symbols, right, or processes. And maybe some other important things too, like how we can communicate more effectively with each other. So I'm going to talk through a bunch of examples now to show you some visual tools. And there's two categories of these. The first one is kind of the landscape or the overview. How do we understand structure and flow and invocations and relationships with the intent of making our code better? It could be to refactor, to maintain it, to develop new features, but just to create positive change in our software. And the second category really has to do with getting into the weeds and the details of things like decisions we make around algorithms or particular, formulas we need to model in our software. You ready? Yeah? Okay. So the first one, we may not think about it while we're writing code, but it's really important to understand structures and flows with the intent that we're always having to learn as we're writing software, and we want to act on what we learn. So anyone ever struggle with understanding packages? Someone has to raise their hand. No? Dependencies? You don't struggle with dependencies? Oh my gosh, maybe I'm just strange. Well, hello dependency graph. This is D3's dependency graph. And this was made using Graphiz and Observable. And this is pretty much as simple as it gets. D3 doesn't have any external dependencies, and it has just a few development dependencies, which have to do with bundling and testing. Some of the complexity comes in because there's like a handful of helper tools. But you can see that top-level dependency to the far left, it quickly turns into spaghetti. So say you're trying to decide what library to use. How do you decide? How do you assess what to use? I mean, of course, we think about the features that we need, but do you think about the types of dependencies that you're taking when you use something and what those dependencies are of the thing that you're taking the dependency upon? Dependency graphs, pretty simple, but an easy way for you to understand more dependencies in what you're using. But what about understanding runtime behavior or data flow of your code? Hello, data flow diagram. So this is an example of a diagram modeling how data flows through code. Each arrow indicates a dependency between two cells. So that D3 cell that I showed you before, you can see it there on the left. It represents the D3 library, and it's referenced by many cells. Makes sense. So this graph is computed automatically using static analysis of the code. But I think the thing that I look at here is when we're writing code and we're developing software, we may sort of think about it in the beginning, but how often do we go back and assess how complexity has built up over time? And these graphs are really a good way for us to visually see and come back to how's the code changing and how's the flow changed, as maybe many more of our teammates have been modifying the code. And here's another interesting way to look at it, which is actually animating the flow of data through the graph. So this is a video of code that's running on live data flow. You can see the order in which the cells run. It runs in topological order rather than top-down. We can automatically rerun cells when code or state changes. And we're kind of stepping through the evaluation of this notebook and able to visually see what's happening. So the previous one, you can visualize statically, but you can also add animation so you can learn the flow of what's happening in your software. What about state management? Right? When we're thinking about the software that we're writing. Well, hello, Graphiz. Graphiz is super easy and great for understanding state machines. parsers, protocols, and data structures like linked lists. So what you're seeing on the bottom is code actually producing the diagram above. So this is a toy example. You have to use your imagination for a problem that you may want to solve in your own work, but each node corresponds to a different state. You know, there's many different ways that we can create diagrams, by hand on paper, or at the whiteboard, or piping data through them, but Graphiz is a really easy way to start tinkering. You don't have to think about the layout. And you can see, right, we're assigning labels to the diagram in the code. We're going to add some formatting here to sort of indicate the state through different shapes. And then we're actually going to be able to see how the state flows. And essentially using visual modeling like this can make it easier when we actually sit down to write code. You could come back and tinker. I mean, I think that took us like 20 seconds to do. Okay, so lots around dependencies and being able to visually see things. What about when we want to understand different types of structures like file systems, files and folders? Hello, zoomable sunburst. I love this one. So this gives you a macro view and then the micro view of individual details. So what you're seeing is basically files and folders with relative size. You can visually see, drill down, and explore, and get a sense of the complexity and size of the software that you're writing or you're accessing. And some of these examples you can just easily fork, add your own data, and make it your own. But it's pretty cool to visually be able to see those relative sizes as you're looking at the structure. But what about if you're trying to understand the structure of your code? What could you use to help you do that? Hello, radial tidy tree. This visualization creates a hierarchical node link diagram. This is the code hierarchy for Flare, which is a visualization framework. So it's modeling the leaves and nodes in code. And I think by looking at it, it's kind of easily understandable, right? You can kind of immediately start to grok what's happening in this code versus moving in and out of directories. If you care about the number of files, you use this, right? Or the types of code that you want to look at. It emphasizes the structure. But if you care about size, right, you can go back and use that zoomable sunburst as an example. Okay, so what about understanding the relationships in the code that we're working with? I think visualizations, one of the many ways that they're really helpful is they can help us find hotspots in our code to sort of like start to detangle the hairball when complexity builds up. And this provides us with opportunities to improve, restructure, refactor our code. Hello, hierarchical edge bundling. I love it. It's so beautiful. This chart shows the relationship among classes in a software hierarchy. Each directed edge going from source to target corresponds with an import. So let's look at some details. So the links go from blue to red. So packages with more blue links have more outgoing edges. They depend on other packages. Whereas the packages with more red links, they have more incoming edges. They're dependent upon by other packages. And the packages with both the blue and the red links have both incoming and outgoing edges. They're really central and tightly coupled. But you could also see where there are a bunch of just only local dependencies. It's pretty self-contained in the code. Maybe that's fine. You don't need to worry about that code. But here's an example of data sprite. It has 24 incoming dependencies. So that data package is pretty central. And I think the thing for us to think about is like, okay, so say we're going to go in and modify that code or access that code. Like understanding its dependencies and visually being able to explore that can really help us with our understanding and what we do next in the code. Here's another example of seeing relationships between core data code. So this guides us, sorry, I have to go back. It guides us to look for places to understand the relationships, decide, do we want to refactor? Do we want to make some coding changes? And I think the interesting thing about using a visualization is sometimes you can be surprised, right? You can find things you didn't know were there. And you can use the visualization to really help yourself understand the relationships between those code and potentially, reduce or minimize those relationships if that makes sense. You already saw this, but it does come in rainbow, which I really like. Okay, so we've talked about structures and relationships and how to view data flow through our code. What about the humans, right? What about the developers? So what if we want to learn more about authors and contributors? Think about open source contributions. So what if you want to understand more about what's happened with a particular library that you're interested in contributing to? Okay, so hello edit visualization. Now this is an old visualization. It's an example of edits in Wikipedia. So each color corresponds to a different author, and we can see the first version on the far left. You can see content being inserted and removed, the black squares. And you can observe how the content grows over time and how it was edited. But do you see that zigzag up there? That's an edit war. Or maybe we should call it like an edit dialogue and discussion, right? So these are authors that keep reverting each other's changes. But it's sort of fascinating to be able to see this and to be able to understand what the humans are doing when they're modifying the content. What about this example? Hello code diff. We've probably all seen various flavors of this, right? Examples of using visual design to improve the readability of git blame for a file in React. So you can see which parts of the file have changed more recently and who the frequent authors are. It's super helpful context for us as we're writing software. Or hello bar chart race. So this is a way to view data over time. So this is 7 years of React development in 30 seconds. It's like mesmerizing. Okay, so admittedly, this is only looking at inserted and deleted lines, which is not a good proxy for value, but you can see the activity of the contributors over time. And it really, you can kind of have some insight into what's happening with this code, who's involved, who's contributing to it. That's fascinating to watch. Is it done? Okay. So that was a bit about the high-level structure and flow and invocations where we understand visually and then we're able to make changes, positive changes in the software. So now I'm going to drill into some details, like really go into the weeds. And there are times, right, when we need to interact and explore when we're making design and implementation decisions. So, for example, how do we understand algorithms? How do we make decisions around the algorithms to use? How do we know it's running? Do we understand when it's done? So, hello, algorithm visualizations. So I'm going to walk through a couple of examples of these just to demonstrate alternatives. But consider the simple problem of generating, random dots on a screen. Maybe you're sampling an image or retracing an image. So one way is just to pick points with uniform randomness, just like math.random over and over and over again. But does this look random to you? Anyone? It's really hard to tell, right? Okay, so what if we care about the points being evenly distributed, right? It's not great. You've got these points where it's too sparse, there's no dots, or too dense, there's too many. So how do we get more even coverage? So this is a visualization that's built modeling the algorithm in code and then playing that algorithm over. So this is a different approach. Each point, we generate 10 random candidate samples in gray, and then we pick the candidate that's the farthest in red from the existing sample in black. And then we just repeat this over and over again. So we're visually seeing the algorithm play out and pick the points for the sampling. So here's what it looks like when it's running. This is Mitchell's best candidate algorithm. The result is more even coverage, less clumping. Look better? Yeah? Maybe? Not sure. Okay. Here's another algorithm that's even better for the task. This is Bridson's algorithm, and it uses a grid to tell when a candidate samples are too close. It makes it more efficient than Mitchell's algorithm. So I'm not going to go into a lot of detail here, but hopefully you can see, just kind of get a sense of how the algorithm's running on the grid. And here's what Bridson's looks like when it's running. It expands progressively out from the middle. And hopefully you can see the difference visually when I run through both of these of how the algorithms are different. So based on what the problem you're trying to solve, you may decide that one algorithm is better than the other. And visualization can help you do that. It can help you explore the algorithm. And here's just a slightly different view where you can see the relationship of the existing samples and the neighboring samples as they spawn out. And this is a variation of Bridson's where it picks the most recent sample and to expand from rather than a random sample, and just kind of goes like wildly picking the points. I think the fun thing about developing visualizations is that you can kind of tweak the code and see the effect in the visualization. So I can see how things are working, and I can write better code. Visualization, it really reinforces our understanding as we're building. And if we incorporate visualization into our process, we can learn and move faster. So a couple more examples. This is one from a developer who's trying to understand and model an algorithm they're using. So this is hello terrain visualization. This is reconstructing a mesh or height map of terrain of Mount Fuji. So it's a visualization of mesh retrieval for a hierarchical data structure that's called right triangulated irregular network. It's a mouthful. You have these two big triangles, and they recursively subdivide when they don't approximate the underlying surface well enough. So this is an algorithm where we can control the level of detail, either less detail or more detail, and then construct the mesh at the right level. This is an example of using visualization to understand different thresholds in algorithms, see where it works and see where it doesn't. And we don't have to just read the code that Vladimir wrote. We can see it actually working on real data. We know algorithms are configurable, right? They take different parameters as input. So by interacting and exploring through visualization, it helps us understand the effects that those parameters can have. So this is an example of an explorable calculator for placing curved labels on weird shapes. This is, for California, the name California, the map of California. So you can see at the top, we're using sliders to estimate how large we can make the text without overrunning the shape's borders. And it just walks the center line, measuring the distance from the center. And this was an example that a developer put together. It's like 6 steps with code. You can copy it. You can, add your own shape and put a label on it pretty easily. But I think it kind of highlights how you can interact to learn as you're working in code. Maybe you want to help people understand the behavior of dynamic systems. So we have a pair of differential equations describing population of mice, prey, and cats, predators. No offense to cat owners or mice owners. But if we change the starting population of the cats or the mice, right, we can see how this affects the population over time. The populations are cyclical, right? As the number of mice increases, the number of cats increases because there's more food. And eventually there are too many cats and the mice population declines, and so do the cats, and then it repeats, right? And so while this may be kind of an odd example, I'm sure there are times when you're having to model formulas or write code that talks about the relationships between certain things. And if you can visualize those first, it may actually help you write your software. So you saw a bunch of examples, top-level structure and flow to help make improvements in your software, and then digging into the details to make better decisions. But there's a final point I want to raise, and that is we collaborate around software, right? It's a team sport. And so sometimes visualizations are helpful to share with others, right? Visualization isn't something we do for ourselves. We want to share insights with other people. So maybe you need to convince your coworkers that your code needs to be refactored before it turns into a gigantic ball of mud. You can use visualization to strengthen your argument. So this chart shows the number of lines of code of a set of React components in Observable, my company's code base. So that big one there is the notebook component, and it needed to be refactored as the application grew a while ago. But the developer put this together on the team, and 2 weeks ago we kicked off a project to refactor it because we knew it was getting bad, but we just didn't know how bad it was. So here's a way that you can actually motivate toward positive change in your code. Or maybe you just want to help people understand a programming language or concepts, right? Here's an example from Julia Evans of the anatomy of a SQL query. Visualizations don't have to be traditional charts. They can be diagrams that have pictures and concepts using color, using text. So I hope you've learned several new powerful visualization tools and some examples that you can walk away and try. But I just want to come back to how visualization benefits us as developers. I think it's fun. I mean, you can watch and interact with code and algorithms. It's fascinating, right? It's much more fun than interacting with a static text file. And visualization helps us see and understand at a deeper level. And maybe we have more appreciation for the code or algorithm that we're using. It helps us learn. By visualizing the output of our code, our understanding of software is more intuitive and accessible. So I have a couple more Brett Victor quotes, so bear with me. But I love this one. Programming is a way of thinking, not a rote skill. Learning about for loops is not learning to program any more than learning about pencils is learning to draw. I mean, how true is that? We as software developers are always learning, always. Teaching is the other side of learning, right? Teaching is one of the most effective ways of learning. And implementing a visualization, it's like teaching yourself. You're placing a stronger focus on intuitive learning rather than that rote learning that Brett Victor was talking about. So it can be easier to internalize and remember having interacted with the code rather than just memorizing it or trying to remember where you were when you were writing what. Finally, it helps us get our work done. By being able to observe our code, it helps our productivity. Through visualizations, we can discover new things, right? Unexpected behavior, surprises that we can then take action on. And visualization can help you get the code right at the beginning. You can see it rather than just maybe guessing about tests. Now, I mean, we still have to write tests, but visualization can be really helpful when you're iterating in the early stages. Faster iteration, more insight in the work that we do. Coding is a way of thinking. Visualization, it helps us improve our way of thinking as we code. We can see it, we learn through interaction. And if we can help humans, ourselves, better understand computation, we'll design better software and do it more efficiently. Ship faster, make our users happier, and hopefully we're a little bit happier and productive. I mean, it's not easy. I can show you a bunch of examples, but right? Data isn't information. You have to transform the data in code to make it meaningful. Like some visual channels are less effective than others. Not all colors are perceived equally, so you need to think about what colors you're choosing. And you can't just like wave a magic wand for visualization. It takes time to do it right. You need to think it through. Also think about the tools that you need in visualization. And I really hope you're walking away today with many more tools in your tool set. My last Brett Victor quote, I swear. People understand what they can see. If a programmer cannot see what a program is doing, she can't understand it. Visualization, it leverages our human visual system to help us think. Remember, brains, finite time. We want to make the best use of both. So seeing is understanding. You know, we're here at GitHub Universe. GitHub has been driving open source software and collaboration in the developer community. It's pretty inspiring. But if we get the right tools to visualize, we can make our software better. We can better understand both the structure and flow and the details. I really hope you consider how you bring visualization into your own software development. So much hasn't been visualized. Really, let's make visualization a core part of how we build modern software. Let's visualize software together. Thanks so much. Thanks for coming. I hope you have a great conference.